Hi, my name is Mohammed Nihal. I'm going to talk about EV ADAS dashboard system, which consists of real-time electric vehicle monitoring and ADAS warning system. Modern electric vehicles generate enormous volume of real-time sensor data, including speed, battery SOC, which is battery state of charge, motor temperature, torque, and range. Without a centralized dashboard, engineers have no way to monitor EV performance and ADAS safety data simultaneously. A single operator cannot track all parameters manually, which include collisions, blind spots, and fault may go undetected. The definition of ADAS is Advanced Driver Assistance System. SOC is state of charge. TTC is time to collision. HL is hardware abstraction layer. UART is universal asynchronous receiver transmitter. Our requirements of the projects are real-time EV sensing, which consists the system shall read input and monitor speed, SOC, motor torque, power and range. The ADAS safety, which include the system shall feature forward collision warning, blind spot detection via three HCSR04 sensors. Vehicle state machine. The system shall execute deterministic transition from parked to ready to driving to regeneration to fault. The fault management system. The system shall isolate fault like motor overheat or SOC and enforce safe states on detection. The telemetry streaming. The system shall stream structured binary packets over UART to a Python dashboard. The tools and development environment we use are STM32Cube IDE, used for STM32 firmware programming and hardware abstraction. PICSIMLAB, an open source simulator used as a hardware simulator environment for Bluepill. And VSPE, Virtual Serial Port Emulator, creates a virtual loop back connection to route UART telemetry data, bringing COM to PICSIMLAB output to COM1 Python dashboard input. And Python dashboard, the environment for the live visualization of dashboard. The system architecture is like sensors. We use potentiometers as sensors, which control acceleration, braking, SOC, and temperature. And in also HC SR04 sensors. Then STM32 Bluepill we use as a ADC to EV ADAS engine, and UR as we had to show output, so we are using UR in 115200 bps, and we are using Python dashboard to telemetry passing to pages. This is the workflow of this project. First we read ADC input like acceleration, brake, SOC, motor temperature, and it is updated to EV updates. Execute every 10 millisecond motor torque, which include motor torque, vehicle speed, battery SOC, power remaining, and range. ADAS updates, which include execute every 100 millisecond updates. ADAS logic, vehicle state machine, fault monitoring, and triggers HCHR04 sensors, which include left, front, and right, generate trigger pulses. Then measures the distance, read echo pulse, convert to centimeters, validated sensor reading, and compute ADAS parameters, time to collision, forward collision warning, and blind spot detection. And the alarms are priority decided, and priority P0 none, and P1 advisory, and P2 warning, and P3 critical. Like there are four alarms which is in priority mode. Then driver alerts like LEDs, buzzers, and fault indication. Like it will show the alerts like in LED. It will show if the HCXR04 sensors are near detecting near vehicles, and if the battery is very low, It will detect fault and it indicates. And you are telemetry, then prepare EV data packets and speed, SOC, torque, power and range. User transmission, like user 115.200 but send telemetry packets. Python parser, read user data, UR data and decode packets and validate data. Dashboard processing, update dictionaries, refresh gauges, refresh warning indicators, and GUI animation. Matplotlib animation refreshes at 10 fps, smooth gauge movement. And live dashboard, like it will show speedometer, battery SOC, motor temperature, range, ADAS, bird's eye view. It will show collision alerts and blind spot alerts. Phases of our projects are: phase one is environment and setup. It will in phase one we studied about STM32 QBD, PICSIMLAB, Python, and phase two GPIO peripherals. We learned about LED buzzers and timers. In phase three we learned about ADC sensors input, potentiometers, and in phase 4 we learned about EV dynamics model, speed, SOC, regeneration. Phase 5 ultrasonics ADAS engine, FCW, BD, BSD and time to collision. And phase 6 fault and alarm system, 4 level priority. We have learned 4 level priority, we updated that. In phase 7 we learned about USR telemetry, 115200 BPS streams. Phase 8 use UR shell live parameter injection. In phase 9 we have done Python dashboard, matplotlib GUI. This is the ADAS engine logic and threshold. Like we can see there is a vehicle EV detected as EV, and there are three sensors HC SR04 in front, both side, right and left. We can if there are three sensors to detect front collision and side collision blind spot detection, and it will show forward collision. It will trigger a warning if distance is 50 centimeter and less, or time to collision is less than 3 seconds, and critical if less than 20 centimeter or time to collision is less than 1.5 second. And it will show blind spot detection. Left and right sensors activate above 20 km per hour. Alert trigger if a vehicle is detected within 30 centimeter. Also, alarm hysteresis built a 300 millisecond hysteresis, three consecutive readings to prevent rapid alarm toggling from noisy sensor data. So, conclusion is success. We have done successful system integration. The project successfully bridged embedded edge perspective STM32 firmware with an application layer Python dashboard, and resulting in a fully functional real-time EV ADAS dashboard. Performance and constraint, we have done successfully verified critical timing requirement, maintaining a EV control loop execution time of less than 5 millisecond, and HCSR04 sensor read time under 100 millisecond. Fault tolerant architecture demonstrated a deterministic vehicle state machine that successfully detect critical fault like SOC is less than 2% or motor is greater than 90 degree, and cut motor PWM within a single loop cycle. And future enhancement scopes are like, while this simulation was successful, future extension could include real hardware deployment and migration from UR to CAN bus integration, and develop a mobile responsive dashboard. This is the main code I have used. You can see the EV dash, and you can see the main code. The main code I have done. You can see there is no zero errors, zero warning. This is the printing part in UART, like collision warning, blind spot left, blind spot right, alarm priority, and flag. This is time 2. This is timer 1. Timer 3 initiative. UART initiative. GPIO. This is the EV control H code. You can see the I have done some editing in the values so that I can get better readings. You can see I have given 300. Even mass factor is 150 and drag coefficient is 0.2 for better reading. Also in EV control C.C I have done. I had to add this because otherwise I won't get any reading. Here you can see these are the EV parameters. These are the thing I have done in this PICSIMLAB. You can see the battery temperature is very high, so the fault is given. Like you can see here, fault is here. It will change once I reduce it. Also, the speed is here is 29.1. I'll reduce if I put brake, the regeneration will be actuated and the torque is minus. You can see once once it updates, yeah, you can see minus 45. It will regenerate the battery. Also if I reduce it, same thing. If the state of charge is very low, it will show a fault. Yeah, fault is given like fault state of charge is very low, the range is 0, state of charge is 0, so the fault is given. Yeah, also if I reduce the brake, it will show 0, brake is 0, acceleration is very low. If I increase it, it will show. Also this is acceleration potentiometer, brake potentiometer, SOC, state of charge potentiometer. This is motor temperature potentiometer. This is the warning indicator, like it will show the collision. uh, this is blind spot left, this is blind spot right, this is the fault indication. These are the ultrasonic sensors. This is for front, this is for left, and this is for right. It will show once I reduce the distance, the collision warning will show. Yeah, fault is also shown. Also if I reduce this distance of left HC sensor, it is also showing. This is for right, it will show. Once I show changes, it will indicate. Yeah, it will show here also, like the distance is very low, so the warning will, fault is 4, alarm is 3, blind spot is, detection is 11, like it will detect collision is 2, like it is less than left is 15 and front is 29, so the it will show 2 collision. Yeah, you can see all faults are there. Also, if I press reset button, it will all change again. Like yeah, you can see the speed is like 20.5. It is increasing. Once I increase the speed acceleration, it will also increase. Speed will also increase. Yeah, 20.5, 20.5. It will increase. I'll show the Python command prompt. Yeah, I have given com1 as Python dashboard and com2 as for com2 as PICSIMLAB port. I used VSPE for that, and I'll show the Python dashboard. This and this. Also, you can see the battery is 53 percentage. It will change once it is in like this. It is showing critical warning because the vehicles are detecting near that it will. Yeah, you can see it will increase. If I increase this, it will also increase the distance. Yeah, you can see the distance is 158. Time to collision is big. It is been updated. Just a second. Yeah, it is taking time. So the it is been updated like 145, 155. Once I increases, the time to collision will, yeah, time to collision will is 99.9 second. Yeah, time to collision is 99.9 second. Yeah, also the speed is increasing gradually. This is for 21. This is 21.7. It will increase gradually only. Also, if I increase the motor temperature, it will also show in this detection also in this motor temperature. It will automatically update the range of this according to the state of charge. Yeah, speed is increasing 22. It is showing 22. Yeah, it will increase gradually. You can see the previous values 28.8, 28.8, 29.8. Yeah, it is gradually increasing. If we increase the threshold, it will increase according to that. Yeah, the warning is showing because the motor temperature is very high. If I reduce it, it will go. Also, the warning here it will go. The fault is shown like 0.0. Fault is showing because the motor temperature is very high. Also, if I press the brake, it will show the brake value, brake percentage I have using. Also, the acceleration I am using. Also, it will show the torque 282. It will show, yeah, torque 282. It will show like then the next torque is reduced because I pressed the brake. It is regenerating like 49 Newton meter. Yeah, it will increase the range and the battery SOC. Speed is gradually increasing because I have pressed the brake acceleration. Once I release the brake, it will increase gradually. It will also decrease as I press the brake. The speed will decrease. Yeah, it is decreasing, like it is gradually decreasing. 22 it came, like you can see. Yeah, here 22, 22, 27, 22.7, 20.65. Yeah, it is reducing. Also the torque is in negative, which means regeneration. Also the it is showing 145. If I increase this, it will go back. Time to collision is will increase. The speed is 22. It is showing the speed history. You can see the speed is gradually increasing. Now right now there is no fault and no alarms. The battery temperature is 50, motor temperature is 56.9 degrees Celsius, which I have given. If I increase or decrease, it will show in this. Yeah, the speed is in decreasing. Speed is 22.1, 22. Yeah, it is reducing very gradually. So the distance from the front is showing like 282 centimeter, 282. It is showing 282. So the dashboard, EV dashboard work is done. I have given the output. Thank you.